I'm Andrew Appel, and I will tell you about maps and operational semantics. One of the things we can do very well with logic is to reason about the semantics of programming languages. In fact, really, that's why logic was invented. And so coq is very good for reasoning about the semantics of programming languages. One way that many people use to reason about semantics of programming languages is operational semantics, structural operational semantics. That's been the common way to do things for about 25 years now. And in fully formal systems like coq, about 15 years now. So we can write down the operational semantics of a programming language as an inductive proposition in coq. And earlier today you heard all about inductive propositions. So what is an inductive proposition? It's a set of inference rules for deriving something, but with the guarantee that anything derivable is derivable from only this finite set of inference rules. When we use inductive definitions to reason about the semantics of programming languages, we reason about the transition from one state of the executing program to another. And very often, not universally, but very often, we can view the states as a mapping from variable names to the current values of those variables. So the idea of a finite map from some finite set or some finite subset of a countably infinite set to some particular range is really useful in operational semantics, but it's actually useful everywhere else in computer science as well. Your key value store is a finite map. Your hash table, your binary search tree, everywhere in programming as well as programming languages, we need to reason about finite maps. So the theory of finite maps is actually quite simple. It will take me only a few minutes to show you the representation of the semantics of finite maps in coq, and then I'll show you an application for them in representation of the operational semantics of programming languages. Okay, so in this chapter of software foundations, we will start using the real coq standard library. In the first few chapters of software foundations, we reconstruct from scratch concepts like the Booleans and lists and so on. We present the inductive definitions of those things so that you can see that they're not magic, they're just inductive definitions like anything else. And then we reconstruct some of the standard library functions, map and list concatenation, app. In these chapters and these exercises, we can import the real coq standard library. So arithmetic on natural numbers, the Booleans and lemmas and functions on the Booleans, strings. Strings are a little strange in coq. A string is a list of characters, and a character is a record of 8 Booleans. And that's kind of fun. Functional extensionality. This is the Leibniz principle that if two functions give equal results on every argument, then they're equal. That's not built into coq's calculus of inductive constructions. It's an extra axiom that we tend to add. That axiom is consistent with coq, and we'll find it useful. And the theory of lists, which you've seen before. Okay, so let's make finite maps that will be useful in the operational semantics of some toy programming language. And the toy programming language is going to have variable names that are strings. Yes?
What is the difference between require import and require export?
Require import. Well, require says, give me access to these things, but then I would have to refer to them by a qualified name. Require import says, give me access to these things so that I don't have to use a qualified name to refer to them. And require export says, whoever imports me also gets this without having to use qualified names. Okay, I don't recommend the use of export very much because it pollutes the namespace of the people that are going to import you more than they might like. So I recommend you use it sparingly. Notice here we're using it sparingly. Okay. In the operational semantics that we're going to do, we have variable names that are just going to be strings. And the state that we're going to manipulate that evolves as the program calculates will be a mapping from strings to values. So we want finite maps on strings. And to manipulate these finite maps, to look things up in finite maps, we'll need to test whether the key that we're looking up is equal to some key that's in the map. And for this we need a way to calculate whether one string is equal to another. String dec is the standard name of the decidability theorem for strings. So let's look here at the type of string dec. Let's do check on string dec. And it says some bool. Let me turn on the notation and do that again. Oops, not print, check. Display notations didn't quite work. Let's try it again. There we go. So, what does this say? For any S1 and S2, which are strings, either S1 equals S2 or S1 is not equal to S2. Well, we sort of knew that. But it's more than that. Right? Either things are equal or they're not. But we can't always test whether things are equal or not. Right? Decidability is the ability to compute whether things are equal or not. This OR is not just the OR of logic written with a backslash and a slash. It's the decidable test for one or the other. And let's examine the type of this thing. So now I'm going to turn off notation again and print out. Right? So this says, for all S1 and S2, which are strings, some bool of these two formulas, eq S1, S2, and not eq S1, S2. So let's look again at what is some bool. I'll print some bool. Some bool is an inductive. It has two constructors called left and right. And the left constructor carries a proof of A. And the right constructor carries a proof of B. So, if I have the witness to the fact that either S1 equals S2 or S1 not equal to S2, you can destruct it. You can ask, you can pattern match on it. You can say, is it left or is it right? And if it's left, it will hand you the proof that they're equal. And if it's right, it will hand you the proof that they're not equal. So this is one of the ways in coq that we can represent the decidability of something. Another way that we could do it is to write a function that just returns a Boolean and then have some lemmas about that function that it returns true if they're equal and it returns false if they're not equal. You've probably seen that before. You could do that in ML or Java or whatever, although without the lemmas. But here, this plays nicely with the dependent type system in a way that I'll show you soon. Was there a question?
What's the difference between some bool and the disjunction data type we defined the other day?
The disjunction goes left or right with different names than left or right, but it doesn't hand you the proof. Right. So it doesn't imply that there must be a computable test. You could destruct the disjunction and it would tell you true or false, but that wouldn't mean anything about the equality of S1 and S2. So let me show you what happens when we destruct the sum bool. First, I'll turn notations back on. Okay, so This Boolean equality string function, beak string xy, is defined as if string dec xy, so if it's left with a proof, then ignore the proof and return true, and if it's right with a proof, ignore the proof and return false. And from this we can prove beak string REFL, which says beak string SS equals true. And so let's look at that proof. We're right here in the proof now. We want to prove that true is equal to if string dec SS, then true, else false. So we know that string dec SS belongs to type some bool. We know that that's an inductive type, so therefore we can destruct it. So let's destruct eq-dec SS. When we destruct the left carries a value. The value is type proof of S equals S. And when you destruct a constructor that carries a value, it puts that value above the line for you. So what is that value? It's called E above the line here. It's a proof that S equals S. And when we destructed it and it went left, then what did we have? We had that if statement. So that if statement turns into true. And here we have to prove that true equals true, and that's easy by reflexivity. But let's look at the other case. We have to prove that true equals false, but the destruct put above the line the proof that S is not equal to S. And so we can destruct it and reflexivity. So, was there a question? Yes?
Earlier, how did you get the text to appear on the bottom?
Okay. So, what I did here, you could say check string dec. And that puts this text here. But what I did instead is I used the menu in coq-IDE, and of course proof general has a similar menu. Query, check. What did I do wrong?
You included variables.
Oh, I included check string dec, query, check. Yes. So that's a way to do these queries like check and print and about without putting text into your file that then coq gives you warning messages about. All right. So we define beak string using string dec, and then we can use the properties of some bool in our proof of these lemmas about beak string. In real life, I wouldn't necessarily use beak string at all. I might use string dec directly in the rest of the proofs I'm going to do, but let's follow this along. So we have these lemmas about Boolean equality test on strings, that beak string xy equals true if and only if x equals y. Beak string xy equals false if and only if x not equal to y. And they're all straightforward to prove. Now let's talk about maps. Let's represent, I was talking about earlier about finite maps. Maps from some finite domain or a finite subset of a countable domain to whatever. And here I'm going to start with total maps, maybe with a default value. So on some finite set of its domain, it gives interesting values, and on all the other values, it gives the same default value. Was there a question?
Just a reminder that please repeat that.
Right, please repeat the question. Okay, so a total map, mapping from strings to A, is just a function from string to A. Well, it could be simpler. And what's the empty map? The empty map on mapping strings to A with default value V is the total map on A that on every string returns V. So we can just make a lambda function. Now, sometimes, suppose we're calculating along in the operational semantics of some programming language, and we store the value 6 in the variable x. So what we want is a new state that's just like the old state. At every other variable besides x, it is identical to the old state, but it maps x to 6 instead of what it used to map x to. So we want to update a map at just one point and leave the other points the same. So update takes a map m, a domain value, a string x, a range value, v, and returns a map. So this is the map that's just like m at every point except x. So what does it do? It takes some key x prime. If x prime is the same key as x, then return v. Otherwise, return m of x. So we're representing these as functions. All right. So here's an example. Take the empty map that on every identifier returns false. Update it so that at true it returns true. At foo it returns true. So this highlighted thing is the map that at foo returns true and every other identifier returns false. Update that map so that at bar it returns true. And that's our example map. Now, let's print this map. Query, print. Well, okay, that's not so useful. It just gives us what we told. Now let's make all sorts of fancy notation for updating maps. This notation, braces arrow D, is the empty map with default value D. So at every point it returns D. And then this AND notation will be to add another, to update whatever map we have on the left of the AND with, at point A, return X. And here's updating with 3 or 4 things or 5 at once. So here's another example. The same example map. It's the default map returning false everywhere, updated with at foo return true and at bar return true. So I claim that those two example maps, example map prime and example map, are equal. But here's an example. Example map prime applied to identifier Baz is false. Proved by reflexivity. How did it work? Well, example map prime is update. Update is test whether Baz equals bar. That's false. So then it went to the previous map, which is test whether Baz equals foo. That's false. So then it went to the previous map, which is the default map, which returns everywhere false. Example map on foo is true. And example map on cooks is false, and on bar is true, and so on. Okay, so I showed a representation of finite maps as functions. We could represent them instead by association lists, and you saw that before, I think. We could represent finite maps by binary search trees on strings. We could represent them. And in all of these representations, they ought to have the same properties. So let's treat finite maps more abstractly. Let's say, all right, suppose we didn't know that they are functions in the representation, but what properties should finite maps have? And so here's the first property. If I apply the empty map with default value v to any string x, I will get v. That's the homework, if you're doing the homeworks in this chapter. Doing all the homeworks in this chapter combined shouldn't take you more than a few minutes. Here's the second property. If I have any map M and I update it at point x with v, so that gives me a new map, and I apply it to x, then I will get v. All right? That's update eq. Update neq says I have any map M, I produce